So we're going to jump into section 5, the precise definition of a limit. And I highly, highly, highly recommend that you start going through the examples in the book. Read the definition. They break down the definition for you. I'm going to do the same thing in this video. And there's other videos that do the same thing. And the question is, why do we need a precise definition of a limit? Because most of our limit stuff has been a little bit sketchy. Just looking at a graph, relying on the computer to do it for us. Hopefully someone programmed that computer right. Video section. So there's another guy that does math really well. He does a couple videos on it. Sometimes it's called the formal definition of a limit. I have my version of it here. Check that out. This takes getting used to, which means you need to look at it more than once. And then there's some practice problems here. So what is the precise definition of a limit? The formal definition of a limit. Let's see. Of a limit. So we take these limits, we say something like the limit as x approaches some number a of this function is equal to this y value L. And sometimes we can just plug in and just get there. Other times we have to kind of look carefully what's happening on each side to try and figure out what L is. And sometimes we can use algebra to get there. So we had 3 ideas about how to determine what the limit was, numerically, graphically, and algebraically. If there isn't an algebra technique, then that means you just have numerical / graphical to go about it. And so this limit kind of gets at that idea. And most limits are, many limits are not algebraically doable. You have to look at it numerically and graphically. And graphical is just a picture of the numbers. So what does it mean to have a limit? That's what this gets down to. And I mentioned before that this x arrow a means x approaches a. And kind of like when the police approach a suspect, they're not necessarily going to touch them, right? That could be dangerous. We're just getting close to take a good look at what's going on. And an approach is to not necessarily touch. Right, so I might not get to actually use the number a because weird stuff happens, like a 0 over 0, which is indeterminate. As x approaches a, if this statement right here is true, then that means y approaches L. Right, so an example of that right there is the fraction 1/3 I've talked about before, which is 0.3333. 1/3 of something is a pretty simple concept. Right? I have one thing, I break it into 3 equal pieces. One of those pieces is a third. But this decimal thing is weird because these decimal values go on forever. So as I keep adding another place, I get closer to the actual idea of 1/3, but as a decimal, I never actually get there. So this list of decimals, it approaches 1/3, but we never actually get to touch 1/3 when we use the decimal version. We're always just a little bit off, right? It's all this rest of the tail that we're missing that we're off by. And the idea is this limit is kind of a dare. And the dare goes, you tell me how close to get to 1/3. Or whatever limit I'm approaching. And then I tell you how many places, how far out you have to go to get there. So that's the idea behind this, that however close you want to get, I can get you there. If this is true, if I can always do this right here, then that means the limit exists. That's the idea behind this. So here's the way it goes. So this has to be true right here. The limit exists right here. And it doesn't necessarily have to be equal to the function value. Notice I did not put f of a over there. Okay. So for every epsilon, that's the Greek epsilon, and epsilon here is just a small y value, or a small change in y, I should say. So for every epsilon greater than 0, there exists a value called delta greater than 0. And this delta here is that's delta, by the way, lowercase delta. Oops, if I could spell delta. And it's a small change in x. So you're getting the annotated definition here. Greater than 0. Let's see, that's supposed to be there. Such that little separator there. If the difference between x and that number a I'm approaching, right? So x is changing, a is fixed. If that right there is less than this little number delta, then f of x, the difference between f of x and the limit in absolute value, because it could be above or below, left or right, that's going to have to be less than, it's not very good, less than, well, go with it, less than epsilon. And we also we don't want to touch a, right? The approach but not touch. So then this right here has to be greater than 0. So I'm going to make a little sketch of what that looks like. So I'm just going to put a little x-axis down here. We'll let this be the y-axis there. And then I have some function. Let's say this is my function passing through f of x there. And then here's the point I'm interested in on that function. And so this right here is a. And then over here would be my f of a. Oops, or no, that's going to be L. So the way the dare goes is you tell me how close to get. That's what epsilon is, okay? So you say, I need you to be, and let's make believe we're really zoomed in here. So I need you to be within this much. That's your margin of error here. And that's that distance epsilon above or below. So that's kind of a margin of error. That's the dare, get that close. And then I can trace this limit plus epsilon over here back to the function and down here, and I can trace this middle here is my L minus epsilon over here is another y value. I can trace that down over here. And what I want to be able to do is based on your dare to get that close, that I can find a range of x values down here, and I can say, hey, pick any x value in this region, and you're close enough to do what you need to do. And the smallest distance down here, you can see that in my picture here, this distance on the left is smaller than the distance on the right. So I would pick that one right there. That distance is my change in x. That's what I'm going to call delta right there. So this is a picture of what I'm trying to do. So here's the intuitive version of the idea of a limit. You tell me how close to get. Like you say, hey, I want to be within 100,000th of 1/3. Great, go right here, and you got it. Go out 5 places or 6 places, but it could be more complicated than that. So you tell me how close to get, and then I do a little magical mathematics, and I say, okay, pick an x value in this range right here, and that will get you a limit close enough to the actual limit. And often we don't know what the actual limit is. There were a couple examples in the homework where we numerically said, hey, it's getting close to 0.7189, but the best we could do is call the number 0.7189. It wasn't like 2 or 1/3, something obvious like that. Let's see, what else do I want to mention? I think I want to break this down some more right there, and then we'll do some examples. So x minus a in absolute value is less than delta. So when I subtract two numbers like that right there, I'm finding their difference. And if I take the absolute value, that means I don't care if it's positive or negative, so that difference is really the distance between them. So what I'm saying here is that the difference between these two numbers has to be no more than delta. So the distance between is no more than, right, less than. And that's a crappy delta. Try again, there's my delta. What does that look like on a number line? Now, x right here, that's a variable. But a and delta, those are constants, they're fixed numbers. So on a number line, the x-axis, a is some fixed number here, kind of like in my drawing before. And I'm trying to find an x value whose distance from a, right, x minus a, so maybe it's this x value, maybe it's that x value, but that distance here, right, this is my distance, it can't be any more than delta. So at the most, I can look out delta to the right. So over here would be a plus delta. And or I could go delta to the left, so that would be a minus delta over there. And so this basically describes an interval. And that interval has a center at x equals a. And essentially the delta is like a diameter, right? That's the distance away, or radius, sorry. And a radius of delta. So from A, look to the right, positive delta, look to the left, negative delta, and inside there are the x values that I want. So any number in here is fair game. Now, because it is a less than, not a less than or equal to, then this would be an open circle there and an open circle there. I can't actually be at the edge. So I want any x value inside that interval right there. So this inequality notation is interval notation. It is, oops, the open interval from a minus delta to a plus delta. Another way to think about that, so I'm going to actually throw some numbers in there. Let's suppose I have a is equal to 2 and delta is equal to 0.1. Not a super small number, but a kind of small number. Then my inequality would look like this. X minus 2 in absolute value has to be less than 0.1. And think way back to one of your algebra courses when you learned how to break this down. To get rid of the absolute value, we kind of use a plus or a minus, but then the minus is going to change the direction of the inequality. So to get rid of the absolute value here, what I have to do is say, well, x minus 2, it could be less than 0.1. And the other option is that x minus 2 would have to be greater than negative 0.1. Breaking that down some more, add 2 to the other side, I get x has to be less than 2.1. And on the same time, x, if I add 2 to the other side, 2 minus 0.1, x would have to be greater than 1.9. And if we think about that on a number line, over here is 2.1, over here is 1.9. And let's shade, say, this one right here in green. So x is less than 2.1. So I'm starting over here and I'm going that way forever. And then this one right here, let's shade that in red. This one says starting at 1.9, open circle. Oops, I wanted to draw that below. Go to the right forever. And the and means they have to overlap. Where do they intersect? Well, they intersect right in the middle, in this region right here. So another way to break down to solve this inequality right here, rather than making two inequalities, you just turn it into a three-term compound inequality. So alternatively, I put the x minus 2 in the middle, and then it has to be less than 0.1 and greater than negative 0.1. And then I can add 2 to all sides. So plus 2, plus 2, plus 2, and I get x has to be less than 2.1 and greater than 1.9. So that's the other way to solve that kind of inequality. So this is something I hope you saw in a past life in math here. This is just fancy interval notation. All right, so let's apply the precise definition in another problem.